Gradient nabla phi tells you how fast a scalar field like temperature or pressure changes, and in which direction it rises the most. Imagine standing on a hill covered with a temperature map. The gradient points uphill and its length tells you how steep the hill is. In Cartesian coordinates, nabla phi equals the tuple of partial phi with respect to x, partial phi with respect to y, and partial phi with respect to z. Divergence nabla.a measures how much a vector field spreads out, a source or pulls together, a sink at a point. Picture a small balloon placed in a flow of air. If the balloon expands, the flow has positive divergence, air is being created. If it shrinks, divergence is negative. Mathematically, nabla.a equals partial a sub x over partial x plus partial a sub y over partial y plus partial a sub z over partial z. Curl nabla cross a captures the tendency of a vector field to rotate around a point, like a tiny paddle wheel would spin if placed in the flow. In fluid mechanics, it represents vorticity. In Cartesian form, nabla cross A equals the vector whose components are partial a sub z over partial y minus partial a sub y over partial z, partial a sub x over partial z minus partial a sub z over partial x, and partial a sub y over partial x minus partial a sub x over partial y. The operator nabla equals the set of partial over partial x, partial over partial y, and partial over partial z. It is called del and is used as a shorthand for these three operations. In other coordinate systems such as cylindrical or spherical, the same concepts exist, but the formulas acquire extra scale factors. The geometric meaning stays the same. The Laplacian is a second-order differential operator that tells how a quantity differs from its local average. For a scalar field phi, the scalar Laplacian is nabla squared phi equals del phi equals partial squared phi over partial x squared plus partial squared phi over partial y squared plus partial squared phi over partial z squared. Think of a temperature field on a metal plate. If the temperature at a point is higher than the average of its neighbors, nabla squared phi is positive, indicating heat will flow out. For a vector field A, the vector Laplacian is defined component-wise, i.e. nabla squared A equals the tuple nabla squared a sub x, nabla squared a sub y, nabla squared a sub z. Equivalently, using vector identities, it can be written as nabla squared A equals del of del dot A minus del cross A. This form shows that the vector Laplacian mixes both divergence and curl, which is why it appears in electromagnetism. For example, the wave equation for electric and magnetic fields. In spherical or cylindrical coordinates, the component formulas contain extra terms, but the underlying idea, a measure of how a field deviates from its surrounding values, stays unchanged. Fundamental vector differential identities. Two identities are true for any sufficiently smooth vector field, and scalar field phi. Divergence of a curl is always zero. Del cross bold A equals 0. Imagine a tiny whirlpool, the curl. No matter how the whirlpool twists, there is never a net source or sink emanating from it. The water circulates locally but does not appear or disappear. Mathematically, each component of the curl is a difference of partial derivatives. Taking the divergence then adds another derivative which exactly cancels because mixed partial derivatives commute, Clairaut's theorem. Curl of a gradient is always 0. Del cross del phi equals 0. The gradient points straight uphill. If you walk directly uphill everywhere, you never go around a closed loop, so there is no rotation. In terms of components, the curl involves differences like partial squared phi over partial x partial y minus partial squared phi over partial y partial x, which are 0 when the mixed partials are equal. Both identities are the backbone of many proofs, for example deriving the wave equation from Maxwell's equations, and are used repeatedly in solving PDEs. Just as ordinary derivatives obey a product rule, the vector differential operators have similar rules when applied to products of scalar and vector fields. Divergence of a scalar times a vector. Del dot phi A equals phi del dot A plus a dot del phi. Interpretation. The total outflow from a region containing a varying density phi and a flow A consists of two parts: the outflow caused by the divergence of a weighted by phi, and the extra outflow created by the spatial change of phi along the direction of A. Curl of a scalar times a vector. Del cross phi a equals phi del cross a plus del phi cross a. The first term twists the original field, while the second term adds a rotation because the scalar field changes across space. Think of a rotating wind field whose speed varies with height. Gradient of a product of two scalars. Del phi psi equals phi del psi plus psi del phi. This is the familiar product rule from calculus, now written in vector form. It tells how the slope of a product depends on the slopes of each factor. These identities are indispensable when simplifying expressions in fluid dynamics, electromagnetics, and elasticity. Laplacian identities. When the Laplacian acts on products or on derivatives, several useful shortcuts appear. Laplacian of a product of scalars. Del squared phi psi equals phi del squared psi plus psi del squared phi plus 2 del phi dot del psi. The extra term with the dot product is the analog of the 2 a b term in a plus b squared. It arises because each derivative can hit either factor. Laplacian of a gradient, scalar to vector. Del squared del phi equals del squared phi. The Laplacian commutes with the gradient because both are built from second-order partial derivatives that can be reordered. Laplacian of a curl, vector to vector. Del squared curl a equals curl del squared a. Again, the operators commute. You may first curl the field then take the Laplacian, or first take the Laplacian then curl. The result is the same. This property is heavily used in deriving wave equations for electromagnetic fields. These identities let engineers swap the order of operations to obtain a form that matches boundary conditions or simplifies the algebra. Nabla cross a equals nabla of nabla dot a minus nabla squared a. Why is this useful? Imagine you have a vector field A that represents the magnetic vector potential. Its double curl shows up in Maxwell's equations. The identity rewrites the double curl as a combination of divergence, a scalar, and the vector Laplacian, both of which are easier to handle. Geometric picture. The first term, nabla of nabla dot a, extracts the part of A that behaves like a source or sink, the compressible component. The second term, negative nabla squared a, removes the spreading out part, leaving only the solenoidal, purely rotational piece. In fluid mechanics, this splits a velocity field into irrotational and solenoidal components, Helmholtz decomposition. Proof sketch, Cartesian. Nabla cross a sub I equals epsilon ijk partial j of epsilon k lm partial ln equals partial I of partial mam minus partial lai equals partial I of nabla dot a minus nabla squared ai, where epsilon ijk is the Levi-Civita symbol, and we use the identity epsilon ijk epsilon k lm equals delta il delta jm minus delta im delta j. The result holds in any orthogonal coordinate system after adding the appropriate scale factors. Laplacian of common scalar functions. Power of the radius. Let r equal square root of x squared plus y squared plus z squared. For phi equals r to the n, nabla squared r to the n equals n times n plus 1 times r to the n minus 2. Example, for n equals 2, nabla squared x squared plus y squared plus z squared equals 6, a constant which matches the fact that a quadratic bowl has a uniform curvature. Inverse radius. Phi equals 1 over r in 3 dimensions, nabla squared 1 over r equals 0 for r not equal to 0. At the origin the function is singular and the Laplacian gives a Dirac delta, used in electrostatics as the point charge potential. Exponential. Phi equals e to the kr, k constant. Using the chain rule, nabla squared e to the kr equals 2k over r plus k squared times e to the kr. If k is imaginary, k equals I omega, this becomes the Helmholtz equation, common in wave problems. These formulas are handy shortcuts. You can derive them by writing the Laplacian in spherical coordinates. Nabla squared equals 1 over r squared partial derivative with respect to r of r squared partial derivative with respect to r, and noting that the functions depend only on r. Real-world analog. The potential generated by a point mass or charge varies as 1 over r. Its Laplacian being 0 away from the source reflects the fact that there is no local mass or charge density there. The field is harmonic. Radial unit vector times a power. Bold f equals r to the n hat r, where hat r equals bold r over r using the vector Laplacian identity. nabla squared of r to the n hat r equals n times n plus 1 r to the n minus 2 over r squared times r to the n hat r equals n times n plus 1 minus 2 r to the n minus 2 hat r for n equals 1, nabla squared of r hat r equals 0. This result appears in the solution of static electric fields from a uniformly charged sphere. Inverse cube field, bold F equals bold R divided by R cubed, equals xi hat plus yj hat plus ck hat divided by R cubed. Direct calculation or using known identities gives divergence of bold F equals 0 for R not equal to 0, curl of bold F equals 0 for R not equal to 0, and therefore Laplacian of bold F equals 0 vector for R not equal to 0. The field is both divergence-free and curl-free, that is harmonic. At the origin, it has a singularity that corresponds to a point dipole source. These vector Laplacians are the building blocks for many physical fields, the magnetic field of a dipole, the velocity field of a point vortex, and so on. Recognizing the pattern inverse cube to harmonic saves a lot of algebra in exam problems. Explanation, typical exam problems and solution strategies. Prove the fundamental identities del cross A equals 0 and del cross del phi equals 0. Write the components using Levi-Civita symbols. Show that mixed partial derivatives cancel because partial I partial j phi equals partial j partial I phi. Conclude the expressions are identically 0. Solve Laplace's equation del squared phi equals 0 in spherical coordinates for a spherically symmetric potential. Assume phi equals phi of r only. Use the radial part of the Laplacian. Del squared phi equals 1 over r squared d doctor of r squared d phi doctor equals 0. Integrate twice. R squared d phi doctor equals c1, therefore d phi doctor equals c1 over r squared, therefore phi of r equals negative c1 over r plus c2. Apply boundary conditions, for example phi tends to 0 as r goes to infinity, to determine the constants. Poisson equation for a point charge. Del squared v equals negative rho over epsilon naught with rho equals q delta of r. Recognize that away from the origin, del squared v equals 0, which gives the solution from earlier. Use Gauss's law to relate the discontinuity of the derivative at r equals 0 to the charge, giving v equals q over 4 pi epsilon naught. Apply the double curl identity to derive the wave equation for the electric field E in free space. Start from Maxwell. Del cross E equals negative partial b over partial t, and del cross b equals mu naught epsilon naught partial E over partial t. Take the curl of the first equation, substitute the second, and use del dot E equals 0 in free space. The double curl identity converts del cross E into negative del squared E, yielding del squared E minus mu naught epsilon naught second partial of E with respect to t squared equals 0. Cartesian to spherical conversion. Verify that del squared of 1 over r equals 0 using the spherical form of the Laplacian. In spherical coordinates, for a radially only function f of r, del squared f equals 1 over r squared d doctor of r squared d f doctor. Compute with f equals 1 over r, derivative of f with respect to r equals negative 1 over r squared, then r squared times d f doctor equals negative 1. Derivative of negative 1 is 0, therefore the Laplacian equals 0. Strategy tips for exams. Memorize the core identities, product rules, double curl, Laplacian of a product, and understand why they hold. This makes it easier to reconstruct if you forget the exact sign. When a problem asks for a Laplacian, first check if the function depends on only one coordinate. Switch to the appropriate coordinate system to simplify. For proof-type questions, write everything in index notation with epsilon ijk and delta ij. The cancellations become transparent. Always consider boundary conditions, for example behavior at infinity or regularity at the origin. They determine the constants after integration. Practice converting between Cartesian and curvilinear forms. Many trick questions hide a simple radial dependence.